In this video, we are going to configure a modal frequency response analysis for MSC Nastran. So here in this window is the goal. We want to get an idea of what the displacement is across a range of forcing frequencies. We're going to do this when we have zero damping, if you will, and then when we have damping, which would be this blue plot here. This is the structure we're working with. You can see we have a concentrated mass here in yellow, and then in blue is a rigid element. We're going to constrain it here at the base, if you will, and then we're going to apply a pressure distribution at the top. Now, here in this text editor, I have a summary of the new bulk data entries we're going to add. Here, let me actually show you what the current bulk data file looks like. So this is what the bulk data file looks like. We currently have it set to perform a normal modes analysis. I think it might actually help if we look at what the normal modes looks like. So let's go ahead and open the post web app. So this would be this would be the first mode. So let's go ahead and look at that. This next mode would be the second mode. And then we have the third mode, fourth mode, and so on and so on. So the assumption is you already have this file created. You could create this file in HyperMesh, FEMAP, Patran, or MSC Apex, but this is a starting point. What we're going to do is the following. We're going to add a few new bulk data entries. I like to think of this as sort of like spells. If you're a wizard or a warlock, you're going to summon all these different spells. For example, say we want to add a pressure distribution. We're going to summon the spell called pload 4, or in Nastran terminology, we're going to define a pload 4 entry. We're also going to define a frequency 1 entry, and our load 1 entry that defines the frequency dependent load, and then two damping tables that are defined here, and then a last table entry that's used along with the frequency dependent entry. And then we're going to talk about how to configure the case control section. So that would be this top part here. So let's go ahead and get started. So the first part of this whole process is defining the frequency dependent load. That would be this expression here. Let's go ahead and talk about how to do that. So first, let's go ahead and copy our input file, and let's create a copy here, and we'll call this modified. And let's go ahead and import it to the web app. So we are going to be using the Soul 200 web app. If you want to follow along, you can visit theengineeringlab.com. At the top right hand corner is a free trial link to the web app we're using today. That would be the pre-post web app. So if you click on the full list of web apps, there is a link called Dynamic Loads. This is going to let you import that bulk data file. And here the whole purpose in this step is to define the frequency dependent load. So here at the top row, let's go ahead and click on create an R load. We are going to be using R load 1. For the excitation, we're going to be doing this for the SPC. Okay, now for the CF term, which if we look back at the quick reference guide, you can see that we want to define a CF term here. So back in this section, we're going to say create a table D1. Here we'll select table D1. We'll go ahead and say range this between 0 and I believe 1000. Our frequency response analysis is going to go from 0 to 100 hertz. But here we're saying, use this table for 0 through 1000 hertz. And for the table D values, let me go ahead and look at my notes here. I believe I have it set to 1, right? Okay, so let's go back here and use 1 and 1. So this is the configuration we want to use. If you want to experiment with this tool a little bit more, you can do things like modify the delay as an example. So let's go ahead and do that. So here 0.125, that might be a little too much. So here on the right, this is what the frequency dependent load looks like from 0 through 100 hertz. If you want, you can change it here in this upper bound. If you want to look at this from 0 through 1000 hertz, you can also do that. Let's go back to 100 hertz. And here I'm going to turn off the delay. The only term we want to define for this exercise is the CF term. So that would be this table entry here on the left. And then here on the right, this is what the actual frequency dependent load looks like. Here on the right are the respective entries for this frequency dependent load. I'm just going to copy these, and I'm going to go back to that modified version of the PDF file, and I'm going to paste them here. So this is our frequency dependent load. Right now it's currently set to use a SPC entry, but we want to use a pload 4, which we'll go ahead and do that in a moment. Okay, so let's go ahead and open up the viewer. Let's go ahead and import that input file that we modified. And let's go ahead and go through the steps now. So let's go back here. We need to add a frequency 1 entry. The frequency response analysis, are we doing the frequency response analysis for 0 through 50 hertz, 0 through 100 hertz, or 0 through 800 hertz? Nastran does not know what forcing frequencies you want to perform the analysis for, so we have to tell it which frequencies we want to perform the analysis for. So here, let's go ahead and do this. Let's go ahead and turn on the concentrated mass in blue, and then the RBE2. Let's change the background color, and then sometimes it's hard to see a yellow line. So here in the color column, we can click this button, and we'll change the color of everything. So we'll click on pre here on the bottom left, and let's go ahead and reset the table and look for frequency 1. You'll notice now we're in the bulk data select entry section. Let's suppose you're in some other section and you kind of want to find the entry we're talking about. You can go to bulk data select entry, and then here look for frequency 1, or you can go to the search table here on the top right. You can look for that entry, and here it'll give you a link to where you can find that entry. So if you click the link, it'll take you here to the same table we were in a moment ago. Now to enter that entry, you click this row, and now you can click on create entry, and you can start creating that entry that defines the forcing frequencies for the analysis. So if you click on descriptions, this will give you a little bit more information. One thing I recommend doing, I recommend going to the quick reference guide and skim or read all the remarks. All the remarks will give you more information as to the capabilities of that entry or spell. So here, if we're a wizard or a warlock, we're saying we want forcing frequencies from 0 through 100 hertz. So here I'll say, okay, start at 0 hertz, go in increments of 0.2, and then use at most 500 increments, which I believe gets you from 0 through 100 hertz. If you click on these arrows here on the top right, this actually shows you a preview of what that bulk data entry looks like. So for example, if I wanted 9,000 forcing frequencies, I would get 9,000 or 90,000 here in field 5. But here we want 500 forcing frequencies from 0 hertz in increments of 0.2 hertz up to 500 increments, which again, I believe that gets you up to 100 hertz. Okay, so let's go ahead and continue on. We have configured the frequency 1 entry. Let's go ahead and define our pload 4. So to do this, let's go back to select entry, and let's go ahead and look for pload 4. And let's enter that entry. Let's create a pload 4. This is our pressure distribution. Here in the far top right hand corner, click on the right arrow. Let's go ahead and rotate the model a little. And let's click the pick icon. This is going to let us pick objects on the screen. So let's go ahead and move this a little bit. You notice that when you click the plus icon to select element faces, the picking sphere is kind of big. Let's go ahead and reduce the size of that to maybe 0.1. So if this model was using units of millimeters, the pick sphere size, the radius is also in millimeters. So right now this picking sphere has a radius of 0.1 millimeters, if you will. The actual units, I don't know if I mentioned this at the beginning, but I should. This example is from the Dynamic Analysis User's Guide. If you look in this User's Guide, there's actually a section called Bracket Model. This is the example we're using. If I look here in the description, they talk about using 3 psi for the load. So I know that this model is using units of inches for length and pound force for force. So let's go back here. So this picking sphere, it has a radius of 0.1 inches. So to add elements, you click on this plus icon. So let me take a step back and repeat this. So we have a pload 4 entry here in this row. We click on this button here, the pick button. It opens this pick panel, if you will. Click on the plus icon, and now you can click and drag the pick sphere and select elements here on the screen. So let's go ahead and do that. Now, if you ever make a mistake, like I did here, maybe these elements here, I do not want to include those. You can click on the subtract button here. That would be this minus icon or button. And then you can drag and click the picking sphere on the elements, and then you deselected those elements. Now, during the selection process, I've accidentally chosen these elements here. I do not want to select these elements, so let's go ahead and deselect those elements. And then when you do this, you get a preview of what the pressure distribution looks like. That would be these arrows here. You can see that the pressure load is being applied to these element faces, and that's not what I want. So let's go ahead and deselect these. And let's go ahead and look at the preview. You'll notice that the arrows, the pressure load is no longer being applied to these elements. Okay, so now let's go ahead and continue on. We can close this now. One thing we need to do, we need to specify what the value is of this pressure distribution. Here, let's close this. Let's open the LBC's display panel. Let's turn off the display labels, and let's turn it on a second time. Let's close the LBC's display panel, and you notice that the pload 4 has a value of 0. So the pressure distribution has a magnitude of 0. Let's go ahead and open the pre-web app again. What you can do here is the following. Here in the top left-hand corner of this table, now quick comment about side scrolling. If you have the horizontal scroll bar on your mouse, you can use that, or you can hold the shift key and use the scroll wheel, and then that will achieve the same thing. Here, what I want access to is the batch all button. Click that, and then here in the P1 column, this is the pressure. So here we'll type in 3 psi. We'll click this button, and when we do that, and here we'll confirm OK, it's going to carry the value of 3 to every row, if you will. Now we go back here, you notice that the pload 4 entry now has a value of 3, or 3 psi. But there's a problem. The load is being applied here on this side of the face, but we want the load applied on this side of the face. That's okay. What you can do, you can modify this to -3, and then click this button to apply to every row. And then we look at the preview. You notice that the preview is now flipped. The pressure load is now being applied on this side of the element faces. So we need to confirm that this pressure load works. So let's open the preload again, or the pre-web app. Let's go to the case control, or rather the solution sequence part. Let's go to configure. Right now you'll see that it's currently set to normal modes analysis. We want to set this to statics analysis. For the case control section, we'll navigate down to the load section, and then we'll navigate down to the load row. We'll click on that row, and we'll say, hey, let's go ahead and apply that load to subcase 1. Let's do, and here we'll click on add HDF5 out. This is going to trigger the output of the H5 file. We'll click on upload BDF and immediately run. We're performing a statics analysis with that pressure distribution. The reason we want to do this is we want to confirm that the distribution is correct. So right now we're looking at the deform shape. We'll click on this green icon here on the bottom right, display shape plot. So this is the undeformed shape. We click that icon again. This is the deformed shape, so before and after deformation. So this confirms that we are deforming this. So let's go back to the pre-web app. let's go ahead and turn this, or let's go ahead and set this a frequency response analysis. Let's go to the case control section. Let's go ahead and deselect that static load. Again, we temporarily perform a statics analysis, but we have changed this to frequency response analysis, and we remove that, or we unassign that pressure load to subcase 1. So we went ahead and configured our pload 4, so we're done with that entry. Now we have to make a modification to our load 1. So let's go ahead and find that entry. Now, just in case you're new to this whole web app, you can go to the search section. You can go here and look for our load 1. Click this link and it'll take you exactly to where that entry is. Now here, we want to use the new pload 4 entry. So before the dynamic or frequency dependent load, if you will, it was currently selecting some other constraint entry, SPC1. But here we say, you know what? Let's not use SPC. Let's use the pressure distribution. Here you can see that our CF term, which would be this TC/RC column, it's currently configured to use that table D1 entry. If you remember, we used the dynamic loads entry to create this our load entry. Okay, so things look okay here. For the type, let's go ahead and remove displacement. So that's very important. Let's go ahead and remove that. Okay, so we're done with our load. Let's go ahead and we're done with table D1. That was created in this web application. So this web app was used to create the R load 1 and the table D1 entry. Okay, let's talk about damping now. So I recommend referring to the quick reference guide for more information on this entry we're going to be using. So there are different ways to supply the damping values. We're going to be using the critical option. So for type, or here, let me actually show you. So let's go back to the web app. And again, let's assume we don't know where that entry is. We'll go to search. We'll type in the name of the entry. We'll click on this link. And now we can create an additional entry here. So we'll set the type to critical. What does that type mean? What does critical mean? Again, refer to the quick reference guide, refer to the remarks. If you look here, let's see if we can find it. Remark 10, I believe, right? Remark 10 is going to talk more about what that option does. Here, we're going to say use the critical option. So then our damping values are actually going to be fractional values of the critical damping values. So here, we're going to be supplying values of 0.2, I believe. Let me look at my notes here. Right, 0.02 actually. So let's do this. Let's go back to the web app. We set the type to critical, and we'll go ahead and add 2 rows here. So here what we're doing is we're saying that for natural frequencies from 0 hertz to 1000 hertz, use a fractional damping value of 0.02. So if the natural frequency was maybe 800 hertz, the damping value would be 0.02. Now, let's suppose that you wanted to make an exception. Say for 300 hertz, you wanted to say, you know what, do not use any damping for the natural frequency at 300 hertz. You can add a new row by clicking this plus icon. So for 300 hertz, you would click this toggle button and you would say skip. Or alternatively, I haven't tried this, but I suspect it will work. You could say that the damping is also 0. So skip and 0 are the same thing in this case. Let's go ahead and delete that second row. So here again, we're saying that for any natural frequency between 0 and 1000 hertz, use a fractional damping value of 0.02. Okay, so let's go back here. And we're done. We're done with the new spells, the new bulk data entries. We wanted to define and apply a pressure load. That's okay. We summoned the pload 4 spell. We wanted this analysis to consider frequencies from 0 through 100 hertz. So what do? We summoned the frequency 1 entry, the frequency 1 spell, if you will. We then a lot earlier in this exercise, we wanted to create a frequency dependent load. We wanted to summon the rload1 spell. Now, all of these entries we've defined, but they're not active yet. We have to then go to the case control section and activate a lot of these commands. So we have to activate the method command, the frequency command. We have to activate the S damping command. So let's go ahead and do that right now. So we'll go to the case control section and let's go ahead and create two subcases. So subcase 1 and 2. I forgot to create one table. So let's go back to the damping table, which was this entry here. Let's create a second entry. And same thing as before, we'll set the type to critical and we'll add 2 rows. And 0 through 1000. Here, I want to perform an analysis that considers damping and no damping. So with damping and without damping. So in this table, I'm going to say, you know what, use damping values of 0. Whereas before, the damping values were 0.02. Okay, let's go back to the case control section. So we have two subcases here. Let's go to the command section. Let's go ahead and turn on the method command. I believe the method command is already on. So if we go to the configure section, you'll notice that the method command here, it's currently pointing to an eigenvalue entry. So the eigenvalue entry is another spell. We're saying, hey, use maybe the Langshos method to extract the eigenvalues. Extract only maybe positive eigenvalues as an example. That's already been done for us, so we'll go ahead and mark that as done. Now, what about the frequency command? So let's go back to select. Let's go ahead and look for frequency. And let's go ahead and turn it on for all the subcases. We'll mark this checkbox. We'll go to configure, and then in the top row, alternatively, you can search the table. We'll go ahead and say, you know what, activate that frequency entry. So that frequency entry again was from 0 through 100 hertz. We're saying, hey, activate that entry. So we're done with that command. We're done with the SPC1 command. We can confirm this by going to the loads in BC section, and we'll go ahead and click on navigate. And if we go to the SPC, we'll click on this row. You notice that SPC1, I see that it's only active for subcase 1. You have a few options here. You can either assign it to subcase 2, or you can assign it to the above subcase, and then it's instantly carried over to every subsequent subcase. So we'll do that here. So we're done with SPC. Let's go ahead and assign the frequency dependent load. So to do this, go back to navigate, look for DLoad, which stands for dynamic load. And here we'll go ahead and assign that rload1 entry to the above subcase level. And then while you're doing this, you notice that the case control section is immediately updated for you. So here, let's go ahead and see the change. This is before we turn on and activate the deload command. And then this is after we activate that deload command. So this ID here, 1000, it's actually pointing. It's pointing to the rload1 entry. Okay, so we're done with deload. I'll get back to displacement in a moment. Let's go ahead and now assign those damping tables we defined. So to assign those damping tables, you have to look for a command called, let's go back to case control commands, and then select, search for damping. And then there are a million ways to define damping in Nastran. These are some of the ways, but what we're looking to do is use this option, the S damping command. So let's go ahead and turn this on. Let's activate it for subcase 1 and 2. Let's go to configure. And here you can search the table for damping, and you'll find that enabled or active command. Or you can just look at row 3. And here, I think it might be easier if we just look at that row. Here we'll say, you know what, for subcase 1, use the first damping table we used. So that damping table has a non-zero damping value, so damping is on. Here for the second subcase, we'll select the second damping table. The second damping table, if you remember, is using 0 damping. So one requirement when you use S damping, it should always be present. I wish we could do something like this. Let's go ahead and look for damping. So here, if you look, let me zoom in. If you look at this configuration, subcase 1 has the damping table, but then subcase 2 does not have the damping table. So the assumption here is that subcase 2 will perform the frequency response analysis with no damping, but actually got errors with this configuration. So that's why I had to also enable as damping for subcase 2. And then I had to create the second damping table with 0 damping values. So that's why I'm using a second damping command here. Okay, so let's go ahead and maybe zoom out a little. Okay, so let's go ahead and look here. We created subcase 1 as damping, subcase 2, then as damping 2. Now let's talk about displacement. So we need to tell Nastran what to output. Do we want accelerations or velocities or displacements? Here, I've turned on the checkbox for the above subcase level. So whatever happens in the above subcase level, it tends to also happen in the subsequent subcases. So here, even though we don't have the checkboxes marked for subcase 1 and 2, since this checkbox is on, it's also going to trigger displacement output for subcase 1 and 2. Now, I believe, let's go ahead and look at this. Okay, so one thing to watch out with frequency response analysis, it's going to output a lot of data. Sometimes, what you see very often when you go on and have your career, we output the displacements for a finite number of nodes. So I'll give you an example. Let's go ahead and create something called a set command. So we'll go to bulk data, select entry, look for set, and here at the top row, let's click that. Let's move this to the right a little. And let's go ahead and create an entry here on the right, and let's click on the pick icon. Here we'll select this node. So this is the node where we will have the concentrated mass. You'll notice that when we select the node, there's a blue circle indicating you selected that node. And let's close the pick panel. And then if we look here, let's go ahead and look at the bulk data entry. This set command is actually a list. It's a list of all the node IDs or the element IDs that you've selected. Now what I can do is go back to the case control section. Let's go ahead and find the displacement command. We here, instead of saying output the displacements for all the nodes, we're going to say output the displacements for the nodes defined on the set command, if you will. So here we select the set 1, which remember has that one node, node 999. So this is a way to limit the amount of data you get in the F06 file or your H5 file. So instead of getting a file that's 10 gigabytes big, maybe it's 1 megabyte in size. Okay, so one other thing, let's actually try and run this. The F06 file will by default include the input file, an echo of the input file. So if we look at the results, all the nodes, all the materials, all the payload 4, this is repeated in the output file F06. What you can do, you can go back to case control commands and configure. You can click on this button called reduce size of F06. And then when you rerun the Nastran analysis, it's actually going to remove, or it's going to suppress the output of that echo, if you will. So if we look back at the F06 file, you notice that there's no longer those entries, the grid, the payload 4, the SPC, that's no longer listed here. So this has reduced the file size of the F06 file. Let's go ahead and do this. Here, when we're done, we can go to result files. Here at the table, we can go ahead and click on the HDF5 Explorer. This is going to go ahead and create some plots automatically for us. Now, what we're interested is in creating a plot for that node where we have the concentrated mass. So I think the exercise here, right? So we want a plot like this. So let's go ahead and look at this. Here, I believe they want the plot in the z displacement. So along the z-axis. So let's go back here. And you notice we have separate tables here. We want to look at this data for the z-axis. So let's go ahead and manipulate that. You can either create the plots separately, or you can create the plots together. So if you go to the very top, here at the far top right hand corner, there's a button called Create Plot. Click on the button, or actually, let me take a step back. Or how about this? I'm assuming you've already used the other web applications. So I'm assuming you've already gone through a lot of these tutorials. So let me give you some examples. If you want to learn how to use the HDF5 Explorer, if you go to the user's guide, let's go and see where that tutorial is. I forget the name of the tutorial. Okay, so if you go to miscellaneous tutorials, there is an extensive PDF file that walks you through how to do amazing things when it comes to plots in Nastran. So here, I refer you to that document. For the dynamic loads entry, if you want to be an expert at creating the rload1 entry, there is also another tutorial for that. So let's go ahead and look for dynamic loads. Oh, it's actually here. So that tutorial is called Creation of Dynamic Loads via rload1 and rload2. So here, if you want to be an expert at that entry, there's another tutorial for that. So here, I'm assuming you already know how to operate some of these web apps. So here, we'll go ahead and click on Create Plot. And then here in the last plot added, you'll see that that link starts to blink. It's telling you that, hey, we created another plot for you. So right now I'm looking at the displacements for forcing frequency 0 Hertz through 100 Hertz. If you remember the frequency 1 entry, let's go ahead and take a look at that. Frequency 1. This was configured to go from 0 Hertz in increments of 0.2 Hertz and up to 500 increments. So that's what's giving you the 100 Hertz. So now we were asked to create a plot for component Z. So here we'll just go ahead and change this to ZM. And let's go ahead and do this. Let's go ahead and turn off the second plot. So this is what the displacement looks like for the at the concentrated mass. So that would be node 99. So let me go ahead and jump out of here. So that would be this node, if you will. And here, let me go ahead and make sure this is being done right. So this node here is node 999. We wanted to know what the response was at that node. So this is the response when damping is on. If we want, we can actually turn on the peak values here. So we have a peak value of about 1.064 at 9.8 Hertz. Now, if we turn on the second plot, this is the displacement response when damping is off. And you can see that the response here is actually higher. It's 3.51. So let's go ahead and turn on both plots. Maybe we'll zoom into this region. So with damping, we have a value of 1.064. With no damping, it's a value of 3.51. So let's go ahead and talk a little bit more here. So if we go back to the pre-web app, or let's look at the post. So let's do one thing. Let's confirm this value actually. Let's look at what the displacements are for 9.8 Hertz. I believe it was, right? 9.8 Hertz. So when you open the post web app, you get to actually pick the domain ID, if you will. The domain ID basically refers to what subcase, what time step, what frequency, what moment in time, if you will, do you want to look at results for. That's what the domain ID is for. Here, I want to look for 9.8 Hertz. Here, Let me go ahead and flip through the pages. So that would be this row here. I'll select that and get the data, but there's a problem. Since we limited the amount of data to only node 999, that's where we only get data for. So let's go ahead and look at that. I believe if I do this, oh, that's not right. So let's do this. Let's turn on more data, if you will. Let's go ahead and go to case control commands. And for the displacement command, you can either try and look for it here. Oh, it's at the bottom, or you can search the table. Here I'll say, you know what, instead of outputting data just for node 999, output data for all the nodes, and then rerun the analysis. And then here we'll go ahead and jump to the results. So we'll close this and manually move over to the post web app. I'll scroll to the top and select the displacement data set, and we'll go ahead and look for that 9.8 hertz. And then here, I'll scroll down a little, and let's go ahead and turn on the ZM. And here we'll look at some data. Surprisingly, you'll notice that we know that it's 9.8. Maybe we could do this. I don't know if this will work, but we'll see if it does. We can turn everything off but the concentrated mass maybe. And then if we go back to the post web app, let's see if this works. I'm not sure if it will work, but we'll see. Right, so it's being a little stubborn right now, but we were hoping to get a data plot here for the concentrated mass. But that's okay. Let's go ahead and turn on everything else. Go back to the post web app. And so here you can see what the displacements are for the rest of the model at 9.8 hertz. Okay then, so I think we're pretty much at the end of the video. Hopefully you found this video useful. Just in case you do have questions, I think you can go ahead and give me a message at this email address. And one last comment. If you want to practice what you saw today, you can practice the same steps by using this web application that you will find at theengineeringlab.com. If you could come to this website, there's a big blue button at the top right hand corner. Click that button, fill out the form, and we'll go ahead and give you access to this web application. And yeah, that's pretty much it. That's pretty much it for this tutorial, rather. I hope you enjoyed it, and as always, thank you for watching.